ideal sources are not a physical object, and so sometimes there are ways that we can draw circuit diagrams using ideal sources that kind of don't make sense, or that would be a mathematical contradiction. So I'll give you an example. So if I had a voltage source, let's say this one was 6 volts, and then I connected another voltage source like this, and I said that this one here was, let's say, 5 volts, then I have a problem, right? This is a contradiction, because I'm effectively saying that this source on the left here is going to do whatever it takes to make sure that there is 6 volts across here. But the source on the right is going to do whatever it takes to make sure that there is 5 volts here. And I actually have these connected together with a perfect wire. Again, in circuit diagrams, these wires are perfect and ideal. So perfect wires connect these together. And so we have here a contradiction, because both sources are trying to set a different voltage. And so this does not make sense at all. This cannot exist. This does not work. So this here is a contradiction. Okay, cannot work, doesn't make sense, because these two voltage sources are kind of fighting each other. Now, there are sometimes cases where you can connect multiple voltage sources together, and it sometimes does make sense. So let me do a different example. So if I had here 6 volts, 5 volts, and I have this connected to some other sort of rest of my circuit, this one is okay. So this one here is all good. And the reason for that is effectively I have 5 volts over here being supplied by this bottom source, and then from here I have 6 volts. So that means I could take my multimeter leads and I could connect them kind of across the 5 volt source, and I would measure 5 volts. I could connect them across the 6 volt source, and I would measure 6 volts. Or I could connect them across both, and I would measure 11 volts, because they just add together. So across here, 5 plus 6, 11, I would get 11 volts across the combination of these sources. So this one is fine. This is no problem at all. You can also have issues with current sources. So for instance, if I had a current source that said there's going to be 3 amps flowing that way, and then I had a current source that said there was 3 amps maybe flowing back that way, right? You see the problem here, right? The first current source is trying to inject current in kind of an anti-clockwise direction, or clockwise direction, sorry, and then this other current source is trying to inject current in an anti-clockwise direction. And so these two things are opposite of each other. So this one here cannot work. This does not make sense. This one is a contradiction. Now, there are other combinations of voltage and current sources which are actually okay. So for instance, if I have, say, a voltage source and a current source connected together in series, we call this in series when they're connected like this, kind of head to tail. This one is okay, because there will be a particular voltage. Let's label them. Let's say this one here is 12 volts and this one here is 1 amp. Then there will be 12 volts supplied by the voltage source, and the current source will supply kind of whatever voltage is needed to produce 1 amp. Again, the voltage that is needed will depend upon the rest of the circuit. But in combination, this is all okay. It means here that we actually know everything about this circuit already. So I actually know that there will be 1 amp flowing around here. I can then quite easily, with the tools that we're going to learn in future videos, I can quite easily analyze this box over here, what other components are in that, and then sort of solve the rest of this circuit. So that combination is all okay. So essentially, if you want to look for whether a combination of sources makes sense. The things that will cause problems is if you have, say, voltage sources that are fighting each other, like the top example. So here we have these voltage sources kind of fighting each other, right? And so that one does not make sense. Or if we have current sources that are fighting each other, like you see here, again, that one does not make sense. If the voltage sources are connected in series, they're kind of supporting each other, that one is okay. And current sources connected in series would be okay if they face in the same direction. So let's take this one and draw a little variant of that. So if I had my 3 amps like that, and then I take my other current source and I turn it around, and I say 3 amps going that way, if I do it like this, then that one is okay, because this particular combination, these two current sources are kind of helping each other, right? They both agree on how much current should be flowing through this circuit, through this loop. And because they agree, it's all good. But if those numbers were different, right, if it was 5 amps instead of 3 on one of them, then I would have a problem because suddenly they disagree. So you're looking for cases where current sources disagree or voltage sources disagree on the voltage across a particular part of that circuit. Now, as far as calculating the power, you're going to be asked in some of the tute problems to calculate power, and essentially we do this same as last week. We use P equals IV or VI. So we use the positive case by the passive sign convention. If the current enters the positive terminal, so this is the same as last week, and we use the negative case if the current enters the negative terminal. So let's do an example. This one is from the textbook. It's assessment problem 2.1, and they've given us this particular circuit diagram. We have here 3 sources labeled on this circuit. So let's just take a moment and have a close look at this. So the source on the far left-hand side, that's a it's a dependent source because it has the little diamond shape and because the label here has a variable. So it's IB divided by 4. So we're going to need to solve for IB first in order to know what is the voltage that will be supplied by this source. We also have a source over here which is labeled as VG, and so this is again a variable that we're going to need. Now they've sort of drawn this in this problem using the symbol for an independent source, right? Just the circle instead of the diamond. And so basically what they're saying there is that this will be a fixed value. So we need to calculate what is VG. We also have a current source over here on the right hand side, which is just fixed value of 8 amps, and we have a variable IB which is labeled, that will be the current flowing in this part of the circuit over here. And so we see this is IB, which is the thing that we need in order to calculate the amount of current that flows, the amount of voltage that is generated by that left hand side source. So part A of this question says, what value of VG is required for this circuit to be valid? So we look here, we have 2 voltage sources. So I have these 2 voltage sources here. Now this only makes sense if they have the same voltage. So that's what I'm going to need to calculate. Now, the way that I would approach this, I recognize over here that I have a current IB, but I also have a current source on that same component, on that same loop, right? And that means I actually can just read off what is the value of IB, because the current source here will always maintain 8 amps regardless, because it's an ideal current source. So in this case, the arrows point in different directions. So the first thing that I would conclude is that IB is minus 8 amps. And I use a minus sign here because the arrow points in the opposite direction to the current source. So minus sign because arrows are opposite. Right? So now I know what the value of IB is. I can now consider what will be the voltage on that dependent source on the left-hand side. So if IB is that, then voltage at dependent source is IB divided by 4, just reading it off the circuit diagram, which is minus 8 divided by 4, which is minus 2 volts. So I have minus 2 volts over there on that that left-hand side. So now I can kind of draw the what I know so far about my circuit. So I have voltage source here, which is going to be minus 2 volts. I have voltage source here, which is my variable VG that I'm trying to solve for. And I have a current source, which was 8 amps. So I look at this combination of voltage sources on the left part of the circuit diagram, and I see, well, this source over here says there's minus 2 volts. And this one here is connected in parallel with that. So these voltages must be equal. So I'm looking at this and I'm thinking the voltages at these sources must be equal, or else I have a contradiction, right? Or else they fight each other. This only makes sense if they're equal. So therefore, I can conclude that VG is minus 2 volts. Now, the part B of this question is find the power associated with the 8 amp source. So if I have here my voltage across my source, and I know from what I've just calculated, I know that this voltage here must be minus 2 volts, then I can use my equation to calculate the power. So part B here. So I consider, do I want the positive or the negative case? So how are these arrows drawn? So I see here the current is entering here this way around. It's coming into the positively labeled terminal. All right, it's positively labeled. That's how VG is written over here. So it's coming into the positive side. So I just want P equals I times V. And I can now substitute in the values. So I know that the current is 8 amps, and I know that the voltage is minus 2. So I end up with minus 16 watts. And so I remember from the passive sign convention that negative power means that we're injecting energy into the circuit. So this is minus 16 watts is the way we write the power, but this is the same as saying 16 watts delivered, and as opposed to 16 watts absorbed. So this is a component which is actually supplying energy into that circuit.